Okay. So, this we have seen. Now, from this equation V bus, then can be I is equal to I bus equal to Y bus V bus, right, Y bus V bus. Therefore, V bus can be made at that your Y bus inverse I bus, right. So, now from figure 2, elements of Y, this figure 2, just hold on, just hold on. Just hold on. Where that figure 2, right. So, from figure 2 you can compute no y1, just now we have seen y11 is equal to, from here only, from this figure only, y11 the capital Y11 is a small y10 plus small y12 plus small y13, right. So, all these y10, y20, y12, the small y12, all small one, small y13, small y23 and small y34, all these are known to you, right. Therefore, you compute capital Y11 is equal to y10 plus y12 plus y13, add all this, it will become minus j 5.75, right. Similarly, diagonal elements y22 is equal to small y20 plus small y12 plus y23, that is minus j1, minus j2, minus j 2.5. So, capital Y22 is equal to minus j 5.5. Similarly, capital Y33 is equal to small y34 plus small y13 plus small y23, that is minus j 25, minus j 2.5, minus j 2.5, that is minus j 30, right. Similarly, capital Y44 is equal to small y34 is equal to minus j 25, right, because this small y34 is minus j 25. Now, capital Y12 is equal to capital Y21 is equal to minus small y12, that is j 2, right. Similarly, capital Y13 is equal to capital Y31 is equal to minus small y13. So, it is j 2.5 because y13 is equal to minus j 2.5. So, minus y13 j 2.5, right. Y14 is equal to capital Y14 is equal to Y41 equal to 0, because line 1 to 4 there is no connection. So, capital Y14 is equal to Y4 is 0. Similarly, 2 to 4 there is no connection, right, no line. So, capital Y24 is equal to capital Y42 is equal to 0.0, right, and capital Y23 is equal to capital Y32 is equal to minus small y23, that is actually j 2.5, and capital Y34 is equal to capital Y43 is equal to minus y34 is equal to j 25, right. So, with this if you form that your what you call from the bus admittance matrix. So, this is your Y bus matrix, right, and it is a symmetric matrix. In general, y I j is equal to y j I. So, for example, y12 y21, y13 is equal to y31, right, and y14 is equal to y41, right. Similarly, all there is a symmetric matrix, right, and this is your Y bus matrix, but here resistance is not considered, right. So, next you take a small example, because in as a classroom study we cannot go beyond 3 bus problem, right, because then a lot of computations will be involved and it is not possible, but 3 bus problem is sufficient, and I will not tell all these things, only fundamentals of this load flow studies, right, how actually one can work out. So, you have to find out the Y matrix of the sample power system as shown in figure 3. Data for this system are given in table 1. So, this is 1, 2, 3, the 3 bus problem, and generator I think nothing shown, only 1, 2, 2, 3, all these things are given, right. So, now the charging admittance we have taken, and how charging admittance will be included I will tell you, right. So, this is the bus code, they write bus code, that is I mean kind of sending and receiving end, bus I to bus k, right. So, it is just one end to another end, one bus to another bus. So, 1 to 2 bus impedance is given Z I k, it is 0.02 plus j 0.06. Assume all are in per unit. A line charging admittance is given y I k dash by 2 half. when you, because you, for transmission line you have to make pi nominal method y by 2 y by 2. So, it is given y dash I k by 2. By chance if it is given y dash I k, then you have to make it half half, right. Similarly, 1 to 3 0.08 plus j 0.24 and this is j 0.025, that is y dash your basically 1 3 I k. So, y dash 1 3 by 2, this is given. Similarly, line 2 to 3, that is z to 3 is given 0.06 plus j 0.18 and here it is 1 2 to 3. So, y dash 2 to 3 actually 0.020, right. Now, question is that before proceeding, that how we will take that line charging admittance. Suppose you have a line, suppose you have a line, you have a suppose you have a this kind of line, say transmission line, right. You have a transmission line, say this one, right. You have more line, it does not matter, maybe another line, right. Suppose this is 1, this is 2, this is 3 and this is 4, right. So, these are 4 1 2 3 4 transmission lines are there. So, in that case what you can this thing, that for this one, this line has charging admittance. So, this side if you take, say this is 2 to 4, right, 2 to 4 we can put say y dash 2 to 4 by 2 this side and this is also y dash your 2 to 4 by 2, this is 1, right. Similarly, say line 3 to 4 also charging admittance. So, for this line also 3 to 4 sorry 2 to 3 right 2 to 3, then here this side also will be, I am putting like this, this side will be half, that your y dash your 2 3 by 2 and similarly this side also. So, this is also your y dash 2 3 by 2, this side also, right. Similarly, 2 to 1 you have charging admittance 2 to 1, that means this is actually here also your what you call, here also you have this one and here also this side also 1 to 2, this side also you have charging admittance, right. So, this should be y dash 1 2 by 2 and here also this one also y dash 1 2 by 2. That means, as bus 2, because of line 2 4 y 2 dash y dash 2 4 by 2 and for line 2 to 3 y dash 2 3 by 2 and because of line 1 to 2 y dash 1 2 by 2. That means, at this point I mean at bus bar 2, say the total charging admittance we can put y 2 0 is equal to y dash 2 4 by 2, right, y dash 2 4 by 2 plus, right, then y dash 1 2 by 2 plus this y dash 2 3 by 2. This will be the total charging admittance. These 3 terms you have to add at bus 2, right, at bus 2. This way you have to consider the charging admittance, right. That means, half you make this, then you sum up all the charging admittance, right. So, this way you have to consider the charging admittance for the transmission line. So, that is why this your what you call this y dash I k by 2 everywhere it is given. That means, if you consider this your what you call this example I am making it for you, that this is just for your understanding, say 3 bus problem it is. So, this is 1 and this is your bus 2 and this is your bus 3. So, this is 1, then this is your bus 2 and this is your bus 3, right. Now, for this case it is given that your line 1 to 2 it is given y dash I k by 2, it is given, the half is already given. That means, your this one what you call this 1 to 2, that is 1 to 2, that means this side I make it like this, that this side, right, this is your j 0.025 0 3. This is actually y dash 1 2 by 2, this is given, right. Similarly, your this side also, because of this thing, this side also, that this is also your this one, that is also y dash 2 by is equal to j 0.3, this side is given. Similarly, 1 2 3 also given, j 0.025, that is 1 2 3, that means this side actually making it here, making it here, that this is actually y dash 1 3, y dash 1 3 by 2 is given, that is 0.025, and similarly this side also you have to make it half half, right, and this is also y dash 1 3 by 2 is equal to 0.25, this is also given, and y 2 3 is also given, that is 2 2 3, that means here here there is y dash 2 3 by 2 it is given, that is j 0.20, this is given, and similarly here also you have to make it, here also you have to make it, this is y dash your 2 3 by 2 is equal to 0.20, right. So, this thing it is half is given, suppose if 2 is not given, then you have to make it divided by 2, right. So, that means your y1 this is your y this is bus 1. So, that means your y your 1 0, this y 1 0, this notation we write, it is y dash 2 1 to 1 y dash 1 2 by 2, that means this line, this side is half, and for this line y dash 1 3 by 2, right. This is actually your this is actually j 0.03 plus j 0.025, this you have to add, right, that will become j 0.55, right. So, these things, these two things you have to add, this way you have to consider the charging admittance, right. I mean all the line you have to consider half half y by 2 y by dash 2, and then you sum it up all, because they are charging admittance. So, that means that charging admittance of that example, right, this example, that y1 0. So, now you have understood this. First one I told you that y1 0 is half y1 3 dash plus half y1 2 dash is equal to j 0.25 plus j 0.3, that is j 0.055, right. Similarly, that y2 0 will be your half y dash 2 1, actually y dash 2 1 or y dash 1 2, they are same, right. So, it is half y dash 2 1, that is 2 2 1, they are same actually, right, plus half y dash 2 3 and 3 2, they are same. So, it is, that is why I am writing is equal to half y dash 1 2 plus half y dash 2 3, right. That is, it is j 0.03 is given, and j, look already it is y dash I k by 2 given, this is actually half values. So, do not divide it by 2 further, do not do this, right. So, this way you will get y2 0 is equal to j 0.05, right. Similarly, for this bus also y3 0 is equal to half y dash 3 1 plus half y dash 3 2 is equal to, they are same, 3 1 1 3 and 3 2 2 3 actually same. So, half y dash 1 3 plus half y dash 2 3 is equal to j 0.025 plus j 0.2020, that is j 0.045, right. So, this is y1 0, y2 0, y3 0 charging admittance computed, right. Now, next you compute small y12, because z12 is 0.02 plus j 0.06 is given, z13 0.08 plus j 0.24 is given, and z23 0.06 plus j 0.18 is given, right. Therefore, this y12 is equal to 1 upon z12, that is 1 upon 0.02 plus j 0.06. So, it will become actually 15.82 angle minus 71.57 degree, that is y small y12. Now, small y13 is 1 upon z13, So Z13 is given 0.08 plus J 0.24. It will become 3.955 angle minus 71.56 degree, right. Similarly, actually data taken in such a fashion such that r by x or x by x ratio for this line parameters takes same, actually ratio is same, only multiplied by some other factor, right. So, similarly, y23 is equal to 1 upon z23 1 upon 0.06 plus j 0.18 is equal to 5.273 angle minus 71.57 degree, right. Therefore, y11, look at this diagram. Therefore, capital Y11 is equal to Y10 will be there, and this line connecting 2 and bus 2 and bus 3, bus 1 is connecting bus 2 and bus 3. Therefore, y capital Y11 is equal to Y10 plus Y12 plus Y13. So, Y10 we have computed and Y12 and your what you call this angle is same. So, Y12 plus small y12 plus small y13. So, it is 15.82 plus 3.955 angle minus 71.56 degree, because all the cases angle same. So, these two are in bracket and multiplying by this angle minus this one, right, because basically it is 15.82 angle minus 71.56 degree and this y13 is 3.955 angle minus 71.56 degree. So, this comes 6.255 minus j 18.704, right. Similarly, capital Y22 that is 22 means y20 plus y21 plus y23, y21 means y12 small y21 small y12. So, it is actually same as before j 0.05 plus this again 15.82 plus, because angle same for all the this admittance line admittances. So, 5.273 angle minus 71.56 degree. So, this also comes 6.672 minus j 19.96, right. Similarly, y33 is equal to y30 plus y31 plus y32. So, it is y30 small y30 plus y13 plus y23 is equal to y30 small y30 is we have computed j 0.045 plus these two term y13 plus y23 angle minus 71.56, because all cases y values angles remain same, right. So, that means 2.918 minus j 8.709, right. This is all diagonal elements. Now, off diagonal elements capital Y12 is equal to capital Y21 is equal to minus small y12. It will be minus 15.82 angle minus 71.56 degree. That is actually minus 5 plus j 15, right. Similarly, capital Y13 is equal to capital Y31 is equal to minus small y13. It will be minus 3.955 angle minus 71.56 degree. This will become minus 1.25 plus j 3.75. Similarly, capital Y23 is equal to capital Y32 is equal to minus Y23, that will become minus 5.273 angle minus 71.56 degree. This will be minus 1.667 plus j 5, right. So, all this then matrix will be, then y matrix will be your this one 6.255 minus j 18.704, then minus 5 plus j 15, then minus 1.25 plus j 3.75, right. Similarly, this one now you can I am telling you can check this one. Now, if you add all these elements, I mean in a particular row, if you add all the elements, you will find that except charging admittance other thing will not be there. I mean in this first one your that is your y10, that charging admittance was just now we have computed, no, where it has gone, just y10 this one, right. y10 is equal to j 0.055, right, y10. So, if you add this all the this thing, first thing this is 6.255, right, and this is your, if you add all this thing, that minus 5 your this 6.255 or this thing where it has gone, that y11 is equal to 6 point. If you add all these things, right, then you will see that your what you call that only charging admittance will be left, all other things will be cancelled. Similarly, your here also, similarly here also, right. All other things will be cancelled. Only thing is that when you calculating it, check the decimal places correctly, right. Then you will find only, and in that case you will assume that your y bus calculation is correct, right. So, this is actually a small example for your y bus computation, right. Next is the bus loading equation. Now, this is that your for you more important for your what we call that load flow studies, right. Suppose now I have told you that that how to add the charge, consider the charging admittance. Now, you consider a bus bar, this is your bus bar, right, and voltage of this complex voltage of this bus is V I, right. So, ith bus is connected to bus 1, bus 2 and up bus n. So, in general we want to make a generalized thing. So, 1 to n is connected. So, admittance of this all these lines, it is y 1 small y 1, y I 2 and up to y I n, right. And current injection at this bus is I I, the capital I suffix I, the current injection, right. And this is that bus, and here the total charging at here the total charging y I 0 is the total charging admittance. That means, for this line also you have charging admittance, this side half, this side half, this side half, this side half, whatever number of lines connected to a bus bar, take the pi model and make it half half and club together, sum it up, and that is actually that represent y I 0. So, this is the charging admittance of this bus bar, right. So, we have taken pi model, that is why y I 0 I am writing is the total charging admittance at bus I. That means, all the lines taken pi representation, and whatever come to this side half of this all, sum it up all, and that is total, that is y I 0 for this bus, right. Now, net injected current I I into this bus I, you can write now, this is at ground, right. So, y this is voltage V I. So, before showing it, so y I 0 V I, right, plus your y I 1 V I minus V 1 plus y I 2 V I minus V 2 and so on up to V I minus V n into y I n, right. So, that means, the net current injection at this bus bar I, right, you can write now, then I I is equal to y I 0 V I plus, so all small y, right. So, small y I 1 V I minus V 1, the small y I 2 V I minus V 2 plus up to nth term y I n V I minus V n, right. Then you collect all the terms corresponding to your V I and V 1, V 2, V n like this. Then I I is equal to y I 0 plus y I 1 plus y I 2 up to y I n, and this is your V I minus y I 1 small y I 1 V 1 small y I 2 V 2 minus up to minus y n V n. This is equation 7, right. So, from this equation from this figure, now you have learned that how to write the current injection, right, very simple actually, current injection, right. So, that means, now you define, now let us define that capital Y I I is equal to y I 0 plus y I 1 plus y I 2 up to y I n, right. So, this one you define, and then capital Y I 1 you defines minus small y I 1, capital Y I 2 you define minus small y I 2 and so on up to capital Y I n is equal to minus small y I n you define. After that you can write I I is equal to y I V I plus y I 1 V 1 plus y I 2 V 2 plus up to y I n V n. This is equation 8. That means, this I capital I we are writing by assuming this all these things, we are writing this equation in this form, right, in terms of capital Y and V. This is equation 8, right. Next, that means, this equation you can write that this equation you can write, right, that I is equal to capital I is equal to your capital Y I V I plus sigma k is equal to 1 to n y I k v k not is equal to I, because this y I V I term we have written outside of this summation. So, that is why k naught is equal to I y I k v k, this is equation 9, right. Now, that when we are talking about that your transmission line characteristic other thing, at that time I showed you that P minus j q is equal to V conjugate I, and I have told you also that conjugate is required just to capture the power factor angle, right, and when voltage and currents are purely sinusoidal, right. So, in that case the real and reactive power injected at bus I, so we can write at a particular bus I real and reactive power injected, that is that what is real power injection, reactive power injection will come later, right, because generation will be there, load will be there. So, at that time we will discuss, right. So, P I minus j q I, that is the real and reactive power injection is equal to, you can write V I conjugate I I, right, at bus I. That means, in this diagram, that if it is I am making it for you, right, for the time being I am making it for you. Suppose this is my bus bar, this is my bus bar, this is the voltage V I, right. We are taking, this is the current injection actually I I, right. So, this way you are taking basically any bus bar if you take, ith bus bar, right. So, I am putting like this, that power injection is, I put like this, real power is P I and power injection is Q I in this bus, right. So, basically that thing your what you call this thing, we can write that P I minus j q I is equal to V I conjugate I I, right, that way. Just to I told you that to capture the power factor angle you have to write like this, that means I I is equal to P I minus j q I upon V I conjugate, right. This is equation 10. So, from equation 9 and 10, from equation this one and this one, equation 9 is I I expression and 10, that means you substitute this I I is equal to this thing, your this this I I is equal to equate with this one. So, what we are doing is this one writing first, P I minus j q I upon V I conjugate is equal to I I, this equation we are writing, that is y I I V I plus k is equal to 1 to n capital Y I k V k, this is equation 11, and k naught is equal to I, right. That means, we can write y I I V I is equal to, this term is equal to this term first minus this term. So, P I minus j q I upon V I conjugate minus k is equal to 1 to n capital Y I k V k, k naught is equal to I, right. So, that means, V I is equal to 1 upon capital Y I I in bracket P I minus j q I divided by V I conjugate, right, minus k is equal to 1 to n capital Y I k V k, k naught is equal to I, this is equation 12, right. That means, we got voltage equation for bus I in terms of power injection P I and your Q I, that is real power injection and reactive power injection, and also that your in terms of your Y I k V k, but here also V I is present. So, that means, it is your V I conjugate this one, but V I also present here. So, we are writing V I is equal to 1 upon Y I P I minus j q I upon V I conjugate minus capital Y k V k, k is equal to 1 to n, k naught is equal to I. V I also present here, but it conjugate, right. So, that means, this is a non-linear equations, right, all load flow or power flow equations are non-linear equations. So, if we want to solve fast this kind of equation, we have to follow that iterative technique, right, that how to solve this. So, generally we load flow studies, of course, that Newton-Raphson method is very common, right, but we will start first with Gauss-Seidel, then we will go for Newton-Raphson, such that you will have a good ideas about this load flow studies, right. So, although Gauss-Seidel method is it takes computational time is more than the Newton-Raphson method. Gauss-Seidel method actually is convergence characteristic is linear, whereas Newton-Raphson method is convergence characteristic is quadratic. So, its convergence is much faster than Gauss-Seidel method, and Gauss-Seidel Newton-Raphson method, the convergence your what you call that computational time, right, in the almost it is independent of that the number of iterations of solving in Newton-Raphson method is almost independent of the dimension of the problem. But in the case of Gauss-Seidel method, that if dimension of the problem increases, then naturally your what you call that number of iterations also much more. But anyway, later we will see that, but this convergence characteristic like Gauss Seidel is linear and Newton-Raphson is quadratic, right, that is beyond the scope for this this thing, right. So, but next we will move to the Gauss Seidel method, but before coming to that, thank you.